I'm using Rydberg formula to calculate wavelength, frequency, and energy of emission. Now, today we'll be learning how to calculate wavelength, frequency, as well as energy of emission radiated using the Rydberg formula. The Rydberg formula, as we can see, is for hydrogen molecule. We have it as 1 over lambda equals to R over 1 over N 1 square and minus 1 over N2 squared, bracket close. Then we have the Rydberg constant with this value 1.09677 times 10 raised to the power 7 per meter. And then for other metals that are heavier than hydrogen, we also have their Rydberg constant. In Lemma series, for instance, there is a transition from a higher level, such as from N2 to the lowest energy level, which is N equals to 1. To calculate the wavelength of emitted radiation, for instance, in the case of Lemma series, where we have a transition from either 2, 3, or 4, or 5 down to 1, which is the lowest, we can input it and then try to get what value we are going to get as our wavelength when there is a transition from N2 orbit to N1 orbit of hydrogen, of an hydrogen atom. See, we have 1 over lambda. You see, and in this case, all we need to do is just to make substitution. We substitute the values that were given unto us into the formula, and at the end of the day, we come out with our answer. You can see how we have 1 over lambda equals to 1.097 times 10 to the power 7, bracket open. We have 1 over n squared, which is 1 squared and 2 squared. Then when you further expand it, we have 1 squared, which is 1, 2 squared, which is 4. Then still, if we keep solving the bracket, we have LCM, which is 4. 1 into 4 is 4. 4 times 1 is 4. And then 4 into 4 is 1. 1 times 4, 1. So by the time we remove 1 from 4, we have 3 over 4. So we multiply it by our Rydberg constant. We have 3.291 multiplied by 10 raised to the power 7 divided by 4. Then when you make wavelength the sort of the formula by cross multiplying, you see we can now have 3.29 times 10 raised to the power 7 times lambda equals to 4 times 1. Then we multiply 4 times 1 is 4, and then to get to calculate our wavelengths, we have to remove this 3.291 times 10 raised to the power 7. And how do we do that? We do that by dividing both sides by 3.291 times 10 raised to the power 7, since it is the wavelength I want to make the subject of this formula. Then after that, we can now go ahead with division. By the time you divide 4 by 3.291 times 10 raised to the power 7, you get 1.215 times 10 raised to the power minus 7. And this is something that can easily be done either using calculator. I've told you some time ago that when you are making this kind of division, for example, you have 4 divided by 3.291 times 10 raised to the power 7. Don't go and say, or don't go and punch 4 divided by 3.291 times 10 raised to the power 7. If you do that, you end up having a very wrong answer. You see, so what you need to do is you say 4 divided by 3.291 divided by 10 raised to the power 7. When you are using calculator, you can also just do 4 divided by 3.291 exponent 7. So when you do that, you will get this answer. You get 1.215 times 10 to the power what? Minus 7. Then our wavelength is 1.22 times 10 to the power minus 7. Now, mind you, the value that we'll be making use of to check what we are doing is in nanometer, and this ours is in presently is in minus 10 to the power 7. You see, so we need to make it minus 10 to the power 9, since 10 raised to the power minus 9 is 1 nano. So by so doing, we can move this standard form here with the points here at 1.22 to become 122 by moving it 1 2. So by the time you move it 2 times, you have 122 times 10 to the power minus 2. For moving it 2 times, if you move it 3 times, it becomes 10. Then if you move it backward 2 times, it becomes what? Minus 2. If you move it 3 times, it becomes minus 3. But if you move it forward, assuming it is 0.1, is 0.122. I want to move it forward. When you move it forward, it's going to be 10 raised to the power 10 power 1 if you move it once. If you move it 2 times, it become what? It become 10 raised to the power what? Power 2. Now that is how you go about it. Then at the end of the day, when you take, according to the law of indices, when you have 10 and 10, you take one of the 10, then we have minus 2. For these times, you put what? Plus, and then minus 7. Let's go ahead. Then we also have this, that our wavelength now is now 122 times 10 to the power minus 2 minus 7. Minus 2 minus 7 is what? Minus 9. Okay, so in place of this 10 raised to the power minus 9, we put nano, because 1 nano is equal to 10 raised to the power minus 9. So at the end of the day, we have gotten our wavelength to be 122 nanometer. So from this, we can conclude that our wavelength fall under Lemma series, and it is in the what? Is in the infrared region and not in the visible region. You remember that we talked about the visible region, which starts from let's say 400, which is normally between 400 and 700 nanometer or thereabouts. So, but for this, we can see it is less than 400. So that means it is falling under. It has fallen below the visible region, which is now referred to as our IR region. Now, our second calculation is going to be on wavelength of light given off by a hydrogen atom when an electron falls from n equals to 2 to n, from n equals to 4 to n equals to 2 orbits in the Bohr model. So write your solution and then bring out your data. We have n1 equals to 2 and n2 equals to 4, and then our Rydberg constant, then wavelength, which is our unknown. So you write your formula and then you try to what? You now input your values and then make wavelength your subject, the subject of the formula. When you make wavelength subject of the formula, that's all. And as soon as it is made subject of the formula, like we have done, you expand, like we have a bracket here, expand the brackets by multiplying through with what we have outside, which is r. You see, if you multiply r by 1, you have what? R over 4. Then you have minus r times 1, you have r over 16. Then from there, we can make 4 and 16. We can look for LCM of 4 and 16, which is our what? Which is 16. So 4 can go into 16. We have 4 times r, that is 4r minus 16 into 16, 1 times r. So by the time we subtract 4r, from 4r, we have 3r. So we now have 1 over wavelength equals to 3r over 16. Then when you cross multiply to make wavelength, that is lambda here, your solution of the formula, you divide both sides by 3r. Divide both sides by 3r. That 3r cancel 3r. The wavelength is now left as what? As the subject of the formula. Then you now have 16 divided by 3 times 1.097 times 10 is 7. Then by the time you do division, just the way we did with our first calculation, when you do 16 divided by this, you get 4.86 times 10 to the power minus 7 meter. You see? And then by the time you got also we did to make it in nanometer, we're going to get 486 nanometer. And from this we can see that it actually falls in what, in the visible region and in the Balmer series, because all Balmer series ends the transition is from higher energy level or orbit towards to the lowest one, which is to N2, sorry, to N2. So and we have that. So that means, so 486 is one of the standard values that we have as for our transition from N4 to N2, and that is what we got exactly. Let's move forward. Now, our third example is applying the Bohr theory of hydrogen atom. What is the wavelength, frequency, and energy emitted that correspond to transition from N3 to N2? Then number 2, name the spectra containing such emission. Number 3, what region of the spectrum? What region of the spectrum is it found? So all you need to do is you recall the formula, then we call the formula. Now there are 3 formulas that are involved here. We have formula that has wavelengths, that has our Rydberg constants, and then we have the transition, the level of transition. Then we have a formula with what, energy and frequency, that connects energy and frequency, and then the Planck constant. Then we have another formula again, which is frequency equals to speed or velocity divided by wavelength. So now these are the 3 formulas that we're going to use in getting answer to this question. So now the first thing you do is you collect the data, like our frequency is not given, frequency is not given, we have to find it, wavelength is not given, we have to find it, energy is not given, we have to find it. But we have 3 formulas that can help us do that. So C is 3 times 0 times 10 to the power 8. Okay, that is our speed, which is also a constant or a standard. Then we have R, which is 1.097 times 10 to the power 7. Then by the time we input the values that we have collected already into the equation, 1 over wavelength equals to Rydberg constant bracket open 1 over n squared minus 1 over n squared 2. Okay, 1 for the lower orbit, and then the other for the higher orbit, 2 and 3. So making 1 over wavelength equals to R, and then 1 over 4, because 2 squared is 4 and 3 squared is 9. So we also have R. Open the brackets, we now have 9, because the LCM of 4 and 9 is 16. So 4 into 36, sorry, 4 and 9 is 36. 4 into 36 is 9. 9 times 1, 9. Then we have minus, put your minus down. Then 9 into 36, 4. 4 times 1, 4. Now by the time you subtract 4 from 9, we have 5 over 36. So then R times 5, 5R over 36. Then we have 1 over lambda, or 1 over wavelength, equals to 5R over 36. When you cross multiply, then we're going to have 5R multiplied by wavelength equals 36 multiplied by 1. So to get our wavelength, then we have to remove 5R, which is on the same side with what, with the wavelength. So divide side by 5R, divide side by 5R. So by so doing, we have made wavelength as our subject formula. So from there, we now have 36 divided by 5 times the Rydberg constant, which is what, 1.097 times 10 raised to the power minus 7. Please take note of that. So times 10 raised to the power what, times 10 raised to the power minus 7. Then when the division is done, we'll will end up having 656 times 10 to the power minus 9. Following the same procedure we used in the first and second example. And then, since we have gotten 565, it also suggests to us that this is within the what? Within the visible region and in the Balmer series. Now, we have calculated our what? We have gotten the length of that is our wavelength. Okay. Then to get the frequency, then frequency is equals to speed over wavelength over wavelength. So we have 3.00 times 10 to the power 8 as our speed or velocity, then divided by what? By our wavelength, which is 556 times 10 to the power 9 is in meter. The upper one is in meter per square, one is in meter. We cannot use this one that is in nanometer. That is in nanometer, because if we write it down, we must put the value of the nano, which is 10 to the power minus 9. That's why we use the point where it is where it's at 656 times 10 to the power minus 9 meter. Then after that, we divide 3.00 by 656, and we got 4.56 times, but that times minus 3 times 10 to the power 8 minus 9. Okay. So because we have 210 here, one is 10 to the power 8 and one is 10 to the power 9. So you take 1 and then you do 8 minus 9. Minus, where do we get this minus from? Is from this division according to the law of indices. When you have divide, you subtract. So after all that, we end up having 4.57 and 10 times 10 to the power 14. Then step 3 is to calculate our energy. And what is the value for the energy? Energy is equals to Planck constant times frequency. And we'll go to the frequency in step 2. So you bring Planck constant, which is a constant, and it is 6.63 times 10 to the power minus 34. Then times our frequency that we just got or calculated, which is 457 times 10 to the power 14. So when you multiply 6.63 by 4.57, you get 30.29 times 10 to the power minus 34 times 10 to the power 14. So at the end of the whole process of solving for energy, we got 1.03 times 10 to the power minus 19. So we've come to the end of the lesson, but we have an activity that you must do to help you understand better and evaluate what you have done. And what is the assignment? We'll say calculate the wavelength, the frequency and energy of an electron emitted from a transition from n equals to 5 orbit to n equals to 2. N equals to 2. So then B, state the spectra containing the emission. 3, mention the region of the spectrum is found. The second one is to calculate the wavelength of transition from n equals to 3 to n equals to 1, and then name the spectral series and the region it is located. So we have come to the end of the class. Make sure you practice as much as you can. Go through the work example, do your class activity, and we have come to the end of the class today. In the next class, we will be discussing and learning a new chemistry and an interesting chemistry concept. Until then, I remain your facilitator, Sunday Ibrahim. Thank you.